When we're trying to quantify the amount of water that goes into a soil, it's a complicated problem because we have all the nonlinearities of the structure of the soil and whether it's saturated or unsaturated. And so it, in fact, is a tremendous challenge, even computationally for numerical modeling, to exactly predict the movement of water in soil. However, a very important capacity for us is to estimate these things, to say, well, about how would we get at this? And one of the most useful models for estimating the water movement in soils is what's called the Green and Ampt model. The Green and Ampt model was developed in was published in 1911 by Green and Ampt, who did their work in Australia. And we're just going to have a couple of really simple assumptions, so assumptions of the model. That the capillary forces act at the wetting front. So what we're saying is, let's just, for the time being, look at a horizontal problem. So let's suppose we had like an irrigation ditch here, and we had water in it. And I want to get the rate of that water movement away from the ditch here. So this is our ditch full of water, and here's our wetting front moving away from that ditch. And so we're going to associate with that wetting front a wetting front potential. So we can call it H wetting front, okay? And that's the head associated with a capillary pull of that into the soil. So we see immediately that the horizontal driving force is just that wetting front, okay? And then the second thing we're going to say is that behind the wetting front is saturated. So we're going to say that this soil is essentially saturated. That's it. That's all we're going to do. The amazing thing is, what if we wanted to calculate the rate at which that wetting front was moving? How would this help us? Well, let's just write down Darcy's law. And it's going to say that the specific flux is equal to, in this case, it's going to be the saturated conductivity, so minus K sat times the gradient in total potential. Here, we have, and we'll just consider this point here, we have the pressure potential is 0. And this point here, we have pressure potential is equal to wetting front potential. They're at the same elevation. So our total potential, as we know, is Z plus H. And here, we're going to have, we can just set our datum here so that Z equals 0. So what this says then, if this has moved a distance, let's say so far it's gone a distance L, okay? It says that our flux is going to equal minus Ks. Notice this is a negative number, so it's going to be H here is 0, 0 minus H wetting front over L. And so this comes down to equals Ks H wetting front over L. So this very simple set of assumptions that we have a capillary force that's driving things at the wetting front, and behind it the system is saturated, allows us to immediately calculate the flow of water into the system. Now, the one last thing I want to make sure that you remember is, let's say that the saturated water content that we call theta sat, right? let's just say it's equal to 1/3, okay, which is a typical sort of number. Then what is the velocity of this wetting front? Remember that the velocity of the wetting front is equal to the flux divided by the change in moisture content. And if we're going from dry to wet, that's equal to 1/3. So it's going to be Q over 1/3, which is equal to 3 times Q. So be very careful to remember that although flux, it has units of length per time, the true velocity of this wetting front is that flux divided by the change in moisture content. And so in this case, it's 3 times higher. So you always want to keep in mind that yes, the flux is measured in length per time, but actually we have to account for how much porosity is there when we actually calculate the velocity of the wetting front. So that's the Green and Ampt model for infiltration is really this simple, and it can be applied in a tremendous number of contexts, including for vertical infiltration, and in the case of global climate models, often is the model used for describing how water goes into the soils around the world.